Okay, so the topic of today's lecture is called Multiview Stereo. And so this is one of the last, I guess this is the last kind of 3D acquisition method that we're going to talk about. And this is the only one that doesn't involve any sort of interaction with the scene, right? So for example, for LiDAR and for structured light, in both those cases, we were pushing light into the scene and looking at the light in a camera, right? Well, I guess for LiDAR, there really was no camera. We were using a photo detector, so we pushed laser spots out into the world. We measured them coming back. And for structured light, we pushed, either a laser light stripe or a laser or a white light pattern into the world, and we looked at that with a camera, right? And so part of the problem with those is that in each case, we're kind of interfering with the scene, right? We're pushing stuff into the scene that wasn't originally there. It would be great if we could do stuff with purely images, right? So we just take a bunch of pictures of a scene and then we use that to reconstruct 3D. And so, as you may know, these kinds of large number of images, kind of passive techniques, have become much more popular lately. We'll talk about a bunch of kind of off-the-shelf consumer multiview stereo stuff at the end of class. So one way to think about this is that fundamentally multiview stereo is kind of a combination of stuff that we already talked about. So we talked about camera calibration in chapter 6, right? So we talked about if you've got a whole bunch of cameras, how do you know where all of them are positioned and oriented in a 3D space just from looking at image correspondences, right? So we know we should be able to solve the camera calibration problem just by looking at images. So we start from the assumption that all the cameras are calibrated. And then we also talked in chapter 5 about how do we estimate a dense correspondence between each pair of images. And so, we talked about that in the context of optical flow and in the context of stereo, right? So you can imagine that what you're really doing is you're trying to simultaneously estimate the correspondence between a whole large number of images as opposed to just a pair of images, right? But still the idea is the same. And so if I know where the cameras are and I know where every corresponding pixel between the pair of images is, then I can just simply triangulate through every corresponding pair and I can get a dense set of 3D points, right? And that's exactly the fundamental idea behind multiview stereo. And so there are lots of different ways to approach this depth or this 3D from images problem. And so I'm just going to highlight maybe a few of these big picture approaches. Let me just say, though, that I think it's still true, although it's getting closer, that something that is purely image-based, no structured light, no laser scanning, is still not going to be as good accuracy-wise as something where you do push light into the scene and look at it, right? So multiview stereo is never going to be as good as something where you put light stripes into the scene or scan the scene with a laser, right? So you can do pretty well, but not like as well. Is that an arm up?
Yeah. So when you say it will never be as good, is that a limitation of this computational power that we have? So
I see.
If we get through more let's say we get through infinite compute power at this problem.
So
could you actually end up with something as good?
Right. Could it ever be as good? So yeah, maybe I should back off of my grand claim a little bit. But let me put it this way. So where do things like stereo, purely image-based things, have problems, right? So say I'm looking at a flat white wall, right? So stereo will never be able to, obtain direct actual correspondences on that wall. The best it can do is make some sort of assumption like, oh, I'm looking at a plane or I'm looking at a surface doesn't change very much. Or you put it this way, suppose you've got some sort of wavy wall that has not enough waviness to generate a lot of shadows and stuff for the stereo to latch onto, but enough that you couldn't really match up points on the wall, right? So that's something that images will never be able to do very well, even if you had super high resolution images. But something like a LiDAR scanner that bounces physically off a point in the surface and comes back to you is going to be able to disambiguate that kind of thing, right? So, I think that when you've got like a highly textured object, that multiview stereo can do very well. And in theory, the limitations for how well you can do are based on the resolution of your input images and your computational power to do the dense correspondence. I mean, it's fair to say that there are lots of so multiview stereo algorithms are generally made to operate on lots and lots of input images, but at the same time, I think that if you really dug down into the details, that those algorithms are also not really well suited to taking 1,000 4K digital cinema images and making a reconstruction, right? I think that computationally, probably multiview stereo algorithms are still, kind of starting by using kind of more tractable image sizes, and they're not using all the images that you have either. So they're probably throwing out a bunch of those images and then using them to get, incrementally better and better 3D. So, I think that if you have the time to spend on it, if you've got great cameras on it, then you could take several days to generate some amazing multi-view shot. But then you have to think about, okay, well, I could have just done that with a co-located camera and a LiDAR scanner or a structured light scanner. It would have taken me a lot less time, right? So that's where the balance is. But I mean, this is not to say that there are a lot of things that you can do with multi-view stereo that you can't do with LiDAR and structured light. So for example, one thing is that you can generate 3D constructions of things that don't exist anymore, or they don't exist in front of you. You just look at archival photos of things, right? So there was actually, this is very timely. There was a great article in the New Yorker this week about Paul Devovec at the USC Institute for Creative Technologies, the guy who has developed all these light stages we talked about a couple weeks ago. And so one thing that he said in that article, which was very interesting, is that now it's very conceivable that you could look at historical film of actors who are either not around anymore or who are 40 years older and reconstruct their 3D facial geometry from purely images, right? You don't need to have their, you don't have to try and make them up to look like they were younger. You can actually see them when they were younger and effectively get a 3D model just from, so I think they were saying there was one, great shot of Harrison Ford from some movie long ago where he basically was kind of rotating his head under nice, even light. It was like the ideal thing that you would do if you were trying to reconstruct just from images alone, right? And so now you could say, okay, I could take that, push it into a multi-view stereo algorithm and get like the 30 years ago Harrison Ford, right? So very conceivable, to the point that, there was some interesting discussion in the article about, actors probably already are saying, well, I don't remember doing that on set, and it's probably because they probably didn't do it on set, and they've been 3D rendered to look like they were doing something, right? And so suddenly, I'm sure that things like your likeness rights are going to become a much, much bigger issue in terms of, what have you been represented as doing, right? You suddenly lose the control over your own body. In some sense, the actor's face and their mannerisms are like the most distinctive thing that they have, right? And if you can actually simulate that somewhere else, you've taken a lot away from them, right? So it's suddenly becoming a very interesting, tricky technical issue. So that's a great article. And so unfortunately, it's not free online, but I really encourage you, if you have a chance, to take a look at it. Okay, so let me just say, first of all, that, just in passing, that so multi-view stereo was kind of kickstarted in the same way that other things like just regular stereo and optical flow were by this multi-view stereo benchmark. So if you're interested in doing this kind of research, just like with optical flow and regular stereo, there is a nice set of data, and these data sets are basically like little tabletop models, basically. I'm not sure if I can, so here's a little model Stegosaurus, right? So the idea is that, someone went to the effort, this was a combination of, I think, Microsoft and Middlebury, to create these very nice, 3D models of tabletop-sized objects with a whole lot of calibrated cameras. And so, for example, here, their full data sets have more than 300 calibrated cameras of this object. And then they also used, I believe they used structured light, the cyberware model laser scanner. So, I think that, they use some sort of laser scanning to basically generate the very accurate 3D models of these objects. So now what you have are, number one, the true 3D object, and number two, lots of calibrated camera images of this object. And this is a way that you can benchmark your data against other people. And so again, just in the same way for these other algorithms, you've seen charts like this before, you have these kinds of things where you have, the ground truth model. Let's see, I guess if I just select one of these guys. Right. So for example, here, what you see on the left is one algorithm's result of a multi-view stereo algorithm, and this is the actual true scan, the ground truth, right? And so you can kind of scroll your way down through different multi-view stereo algorithms. Like this one is a little bit, not as detailed. These are a little bit, finer detailed. And so, the idea is that you can kind of upload your results. And these days, again, to be taken seriously as a multi-view stereo paper, you basically have to compare yourself against these standard data sets. Also, there is another benchmark by Strecka et al. That is much more like large outdoor scenes. So instead of just looking at something that's like something on a turntable just in front of you, they did benchmarking for like building scale scenes. And so again, if you're interested in doing much larger scale multiview stereo, then that's the data set that you should be benchmarking on, not this smaller one. Okay, so let me talk about 4 basic techniques. And I'm going to spend most of my time, I think, on the first one and on the third one. So the first one is what I would call a volumetric method. And so this is actually kind of related to the visual hull idea that we were talking about in the context of markerless motion capture, right? So if you remember from that lecture, so this I'd say volumetric methods. Right, so you guys just turned in this homework on, kind of silhouette-based estimation, right? So the idea is that, okay, I see the object out here, and I look at this object from multiple perspectives, and I obtain different silhouettes of that object. And the idea is that I can do 3D reconstruction by kind of, let me just make this a little bigger, sorry. I can do 3D reconstruction by kind of coarsely voxelizing the space, and then starting to ask, okay, so which voxels in the world are consistent with my images of the world, right? And so unlike the silhouette and edge-based, so we talked about the visual hull, right, in the markerless motion capture lecture. And so the visual hull starts only from kind of like this binary silhouette in each image, and it pushes that binary silhouette forward in space and looks at where those things intersect and says, okay, so the true thing must lie somewhere within this set of 3D voxels, right? So the kind of twist for multiview stereo is that instead of thinking about just the silhouettes, we think about the actual images that we saw, right? So the idea is that, let me go back to my little figure here. So what I would do is I would say, okay, let's think about this voxel in 3D space, right? What I do is I have all the calibrated cameras already, so I project that voxel back down into each camera view, and I ask, okay, did I see roughly the same color in each of the 3 camera views? If I did, then that voxel in 3D space is a good candidate to actually be truly there. If I didn't, so for example, if the cameras see like red, green, blue instead of red, 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 they say, well, this voxel can't be actually a true voxel because the cameras all didn't see the same color, right? And so you do that kind of modulo expected little color changes. So instead of just looking for a direct 100% match, you kind of have a cost function that says how similar are the n voxel colors that I saw, in space. And the other thing is that, you do allow for things like this. So in this case, this camera, so suppose that the gray, thing of voxels was the true object, right? So in this case, you have to allow for the fact that some of the voxels on the object may self-occlude, right? So if I have some sort of a well, even here, this object is still convex, but from this perspective, this camera sees this voxel here first before it sees that voxel. So this camera doesn't necessarily have to agree on the coloring of this voxel. And so the idea is that you start to consider the voxels in a very specific pattern. And the initial voxel coloring approach, you had to also have a kind of a specific configuration of cameras to prevent bad things from happening, right? So the idea is that you kind of pushed your way through the voxels, starting close to the cameras, and then kind of pushing this plane of voxels away from the cameras. And at every point, you'd look at all the voxels in the plane, you'd say, okay, which of these guys is consistent with all of the pictures that I saw, right? And so that was a little bit restrictive, but that was the first approach. So, the first approach was voxel coloring. By Seitz and Dyer. That was followed by something called photo consistency, or the photo hull. So the photo hull, that was Koutourakos and Seitz. And so the idea there was that basically you're trying to find the largest set of colored voxels in the world that are consistent with projecting those down into each of your calibrated camera images, right? And so the idea is that, it's kind of similar to carving away voxels that can't possibly be consistent. And so, these algorithms are kind of almost what I would call classical. I mean, part of the problem with them is that you have to very finely voxelize up your space. And so that means if you want like a super high accurate scan, like if you want a millimeter accurate scan or a sub-millimeter accurate scan, you can imagine that your working volume is necessarily restricted by just how much computational memory and horsepower you have. And so the other thing is that in some of these earlier techniques, you were, you want to make sure that you don't do anything that you later regret. So for example, if you were to remove a chunk of voxels that later you found out that, oh, you made a mistake and you needed those voxels, hard to get those voxels back, right? And so there have been some modifications to these kinds of voxel carving and voxel coloring algorithms that don't let you recover from mistakes, or in some sense you can imagine kind of solving kind of like a graph cut problem, like a huge multi-label graph cut problem where you say, okay, the label for each voxel corresponds to kind of a discrete disparity or discrete XY position in each of the source images. So you have like this huge multi-label set that you could solve with some sort of like massive alpha expansion problem, right? So yeah, I think that, one of the nice things about these volumetric approaches is that, unlike the methods that we're going to talk about next, they don't necessarily depend on any initial understanding about correspondences between the images, right? So they just look at where are the cameras, and they start to push this plane of voxels through space and start to chew away 3D space until you've got something that is a colored set of voxels that's consistent with these images, right? Some of the methods we're going to talk about next are going to be much more, they're going to leverage the ideas behind sparse and dense correspondence much more. And consequently, those are the ones I think are really the top performing multiview stereo algorithms now, are the ones that are really using the correspondences that you get from something like SIFT or feature matches. Okay, so like I said, volumetric methods I think are one of the first methods that people kind of looked at to approach this problem, but not what I would say are currently necessarily the best methods. So there's also what I would call surface deformation. And so, surface deformation methods kind of inherit their methodology from an old image processing computer vision algorithm called snakes, or active contours, right? So basically the idea behind an active contour is that, if I have a object in an image that I'm trying to segment, what I do, this is a tree, by the way, what I do is I basically build what looks like kind of a flexible rubber band. And so what I have is kind of initially a set of edges connected by these vertices. They call this an active contour or a snake. And the idea is what I do is at every step I allow my vertices, my snake, to kind of try to wrap tightly around an object, right? And so the idea is that you try and build a cost function so that the edges of the snake are attracted to image edges, right? So when the snake is out in the middle of a flat region, it is kind of compelled to move towards somewhere where it's hitting an image edge, right? So the idea is you want to push these guys in closer to image edges, and there are various ways of, kind of attracting these guys with this inward force until at the end they wrap tightly around the object that you care about, right? And so this was a very common way to do image segmentation for a long time. And one of the things that is tricky is that number one, you need to have a large number of nodes to be able to kind of wrap really tightly around this object. So for example, for my tree example, if I just have like 20 nodes, I'm probably not going to get a very conformal wrap around my object if I'm forcing things to be just straight lines between the edges. So maybe I need to have 200 points on my snake instead of just 20, right? And so there's also a little bit of a trick in terms of how do you keep the topology of this thing from, being from staying a nice, simple, closed curve, right? Because you can imagine that if I have something that's got like a narrow, isthmus between two regions, that it's possible that the snake could kind of cross in on itself, and that would be bad, right? So maintaining the topology of this, especially when the nodes get really close together, can also be a headache. And so really the way that people would solve this problem now would be, instead of using a literal snake, what they use is called a level set. And so the idea behind level set image processing is that instead of trying to push this curve around, what you do instead is you say, okay, if I'm trying to segment, say I'm just trying to segment this circle, right? So what I do instead is I say, okay, instead I try and estimate a function of x and y so that this function is exactly 0 around the boundary of the thing that I'm trying to estimate. And inside the object, it's negative, and outside the object, it's positive. And so this kind of gets around a lot of these things about keeping track of how many vertices I need and crisscrossing of the edges of the snake and stuff like that. The downside is that really to do this problem, you're kind of back to a volumetric method where you have to kind of discretely voxelize up the space, and then once you know what this function is, every voxel in the space, you extract all those voxels that have basically 0 values of the level set. So again, this is not to say this can't be done. This is a very common thing to do, but it is still kind of a volumetric thing where you have to make choices about how dense is your voxel grid and stuff like that. And so how does this relate to multiview stereo? Well, the idea is that instead of having a one-dimensional contour, instead what we have is like a 3-dimensional triangle mesh that is wrapping tightly around the object in the world that we want to build a nice model of, right? And so the idea is that you start with maybe some really simple triangle mesh, like maybe you have a very nice sphere that you put right around the object in space. And then you start to deform the vertices of those triangles until it kind of wraps around the 3D object that you're trying to segment in the world. And so what you need is basically some sort of a cost function that says, S is some sort of, for example, triangulated mesh, or kind of a level set version of that. And what you try and do is something like, okay, I want to minimize the energy of the surface where there are a bunch of terms. So I have some measure of how well the surface matches up with each of the images, and then I have some measure of, kind of similar to the motion, to the markerless motion capture, where I can say, okay, I need the silhouettes of the surface to project down to the silhouettes on the images. And then you usually have also what's called an internal force. This internal force is something that keeps the snake kind of, as tight as possible, right? So, I mean, you don't want a snake that is too, loosey-goosey. You want something that's always going to be compelled to get the tightest boundary around an object that it can, right? So usually try to have a force that is always kind of pushing the snake to conform to something, right? And so let's just talk for a second about, so we already kind of talked about this guy in the markerless motion capture section. This is kind of like something you can think of as kind of always, pushing the snake to be tighter. And then what is this thing? So this is basically saying something like, how consistent is the surface with each of the images? And so, again, there are different ways to do this, but the easiest thing to do would be to say, okay, I have some surface, and let me actually, I think I have a better picture of it than what I can draw. So I have some surface. This is, for example, my candidate triangle mesh, right? And what I do is I say, okay, I'm going to take a patch over in one image, I'm going to project it onto the 3D surface, and I find out where that patch land over here, and then I would have this dotted line box. And then what I could do is something simple like the normalized cross-correlation between every, for every box I draw in one image, I can find out these dotted line boxes in all the other images and figure out what the cross-correlation is between each of those things, right? And so if the point on the surface is good, then I expect that when I project it back down the images, that the patches all kind of agree, right? One thing that you have to be careful of, though, and this is another way of illustrating it in this picture, is that you don't usually want to match square patches in one image to square patches in the other image, right? We had a picture long ago where we kind of showed that what's square in one image looks perhaps very non-square from the other image. And so what you can do is you have this triangle mesh already. You have a candidate triangle mesh, and you kind of use that mesh to mediate what you should be comparing. So you say, okay, this is my candidate. What I do is I take this rectangle, I push it up onto the mesh, I find out where does that rectangle hit my mesh. That gives me some weird 3D chunk of surface. Then I can project that weird 3D chunk of surface back down onto this other image, and then what I do is I compare the solid square here to the solid weird shape in the other image. And so the idea is that I should really be using the expected surface to tell me what the right set of pixels is to compare, right? And so that kind of idea of using the reprojection of the square onto the surface and then projecting it back down onto the image, so I'm not just comparing squares to squares, I think is definitely an important aspect of getting a surface-based deformation model like this to work. Again, you can be a little bit, if you don't want to figure out necessarily this weird non-standard object, at the very least you could kind of tell, okay, instead of comparing this to a square, maybe I should compare it to a skinny rectangle or a fat rectangle, depending on the kind of tangent, kind of based on these angles, I can tell, will this square here project to something skinny over here or something fat over here? And I compare it against at least a family of possible correspondences instead of just the original square. So again, one of the disadvantages of this technique, again, is that, number one, since you're generating this kind of, you're evolving this 3D mesh, on the plus side, your resulting 3D reconstruction is not going to have any holes in it, right? Because your original spherical, initialization didn't have any holes in it. So you're basically just pushing the mesh in until it kind of matches up with all the stuff in 3D that you saw. And that's nice because, one thing that you'll see in other multiview stereo algorithms, like what we're going to talk about next, is that often you do have some sort of a missing data problem, where if you just don't have good correspondences, you end up with missing points in the 3D world. And so this kind of gets around that by wrapping this kind of, chunk of triangles around 3D space. On the other hand, though, this is not really the right thing to do for a non-tabletop-y kind of scan, right? So for example, the scans I showed you here, for the multiview stereo, these are going to be okay for doing a volumetric-based method, right? So for example, the stegosaur is basically, I don't think that the stegosaur actually has any holes in it in the sense of, topology. The temple does have holes in it, but that's okay for volumetric methods if you're using a level set. So level sets can tolerate holes in the objects. And so that's another nice thing about using this level set approach. But that being said, if I'm looking to do multi-view reconstruction of a scene like this classroom, right, where there's lots of independent surfaces, lots of holes, definitely things are not part of one object, then this may not necessarily be the best way to go. Okay. So what then are, kind of the currently top performing multi-view stereo algorithms? I think that it's fair to say that they're generally based on what I would call patches. Okay, and so there's a very well-known kind of family of algorithms that started with what was called patch-based multiview stereo. And so patch-based methods, I would say, are these days highly competitive. And so the idea is pretty simple, right? So again, the setup is we have a whole bunch of calibrated cameras, and we can do things, for example, like estimate feature points like SIFT and SURF and so on between each of these cameras, right? So what we do is we assume that we have a whole bunch of cameras calibrated, and in each camera, say we have a bunch of, corresponding features. This is going to be a kind of a crappy picture because I didn't really plan it, but that's all right. So the idea is, just imagine that's a straight line there. So the idea is you could say, okay, well, for every bunch of features that I can really accurately match up between my set of images, I could triangulate through those points to get a single 3D point in space, right? And again, when you've got lots and lots of images of the same scene taken from, not like super differing points of view, you can generate a large number of sparse feature matches, right? So this is very much like, SIFT, we talked about, or Harris corners, right? So the idea is that first we generate lots and lots of sparse feature matches between all the images in our set. And then we triangulate those out into 3D space, and we get a whole bunch of sparse 3D points. In some sense, this is exactly like the result of structure for motion, right? So we talked about match moving. What are the two parts of match moving? Number one, we recover the 3D camera positions and orientations, and number two, we recover sparse 3D point positions, right? Which is exactly what you guys discovered on your match moving homework, right? Where you had not only the 3D camera path, but also a bunch of 3D points in space, right? And so those are the beginning point for a patch-based algorithm. And so what you do is, okay, so then for every point that you can kind of successfully triangulate out there in the world, you build a little patch. So, like this. So you initially triangulate some point in the world, that becomes your initial center of a patch. And then you can also estimate basically, so here what I've done is I've kind of drawn this like a 5x5 set of points in space on the patch, right? So I estimate a center and a normal for the patch, and then I kind of make a grid on that patch in the 3D world. And then I can project that grid down into each of the corresponding images that see that patch, and then I can do a little optimization problem over the center and the normal of the patch. And so what I do is, for every good sparse feature point that I have, I generate a little patch of texture in the world, and then I basically try and iteratively move the center and the normal of this patch around so it matches up as well as possible with what gets projected back down into the images, right? And so the result is that basically corresponding to kind of like every good point that I would have gotten from something like structure or motion, not only do I get a 3D point, but I get a little oriented piece of texture, right? Just a little square out in the 3D world, right? And so what I get is, at the end of this process, not just a cloud of 3D points, but I get a cloud of little textured patches out in the world. Okay, question?
How do you determine the normal of those patches?
How do you determine the normal of the patches? So one way to think about it is that first you kind of think about where is the, so one way of doing it would be say, okay, let's find the best image of that patch in the world, right? So for example, maybe you would say, okay, I have a reference camera, and I could just say that the first candidate for the orientation of the patch is the normal that points from the center of the patch back towards my camera, right? And that gives me an initial estimate of what that patch should be. So the point is that I'm iteratively refining the orientation of that patch as I go, right? So all I do is initialization. And so usually the initialization could just be the normal that points back to one of the cameras.
Okay.
Does that make sense?
Sure.
I mean, obviously I don't want to make it like perpendicular, or I don't want to make it like parallel to, or I don't want to make it perpendicular, I want to make it as front on to the image plane as I can, right? So the idea being that I'm assuming that a good patch of image texture kind of corresponds to some nice kind of frontally parallel surface out there in the 3D world. Maybe it's not exactly parallel to my image plane, but it's kind of close enough that that gives me a good place to start. And then I start to...
What I'm asking is because wouldn't SIP features and other sorts of features like that be maybe things that are on the edges of things?
Right. So that's a good point, is that, what if, well, but the idea is that if I had a feature match, or if I had a feature detection that was on the edge of something, then the idea is I wouldn't be able to match that very well to the other images. Because, for example, if I have a SIF feature that's on the edge of a building, half of it is on the building and half of it is like background behind the building, then if I see that from another point of view, I'm never going to get a good match in the first place, right?
Understood.
And so those get thrown out. So I only see this process with really good matches. Okay. That being said, I will talk about next time how can you deal with matching when you've got something that's half on, half off the surface. And so we'll talk about that a little bit more when we talk about registration of 3D objects next time. That's a good question, though. So the idea is that once I have the initial set of patches in the world, that's still pretty sparse, right? So now what I want to do is I want to make a dense set of matches. And what I do is I say, okay, so let's suppose that this light gray pixel was one from which I had a good match, right? So I kind of say, okay, that's this corresponding nice 3D square out here. What I can do is say, okay, for the pixel next door that didn't have a good SIF feature, what I can do is I can project out into the world a ray until I meet up with the plane defined by the patch of this guy. So that kind of means that I'm extending this light gray plane out into the world, and I see where does the ray through that intersect, and then I generate a candidate, darker gray patch, that has this center and the same normal as the other guy, and then I start to move that patch around, right? And so the idea is that, I flow my correspondences out from, good sparse correspondences out to places where I didn't maybe necessarily have good SIFT matches, but I'm pushing those patches out into the world, right? And so the idea is that I kind of am, seeding the world with good patches from something like SIFT, and then I'm pushing them out with estimates, kind of under the assumption that I have surfaces in the scene that are not, too different from each other, that are relatively contiguous, right? And so, obviously, to get this to really work requires a lot of careful programming, but that's the basic idea, is that fundamentally, at the end of the day, you go from a sparse set of little patches to a dense set of little patches, and then you can use something like the algorithm we're going to talk about next time to turn all those little patches into a more contiguous 3D model. But this is really the key idea behind some of the cool stuff that's been coming out lately. For example, one of the best researchers in this area, Yasu Furukawa, let's look at this guy here. So basically, this is what you do if you have lots and lots of tourist photos of a certain place. And so here they've got, the Colosseum, and I may skip around this video, so apologize to Yasu for this. But, you get like these very highly detailed, surface meshes, and then I think you'll see as you zoom in kind of how, then once you've got the 3D, then you can relight the model that matches up with a given photograph or a given position of the sun at a certain time of day. And so, the relighting of the scene also really sells the idea that this is a 3D model. So this is an original picture, this is a rendered picture that kind of matches up with that as well as possible. And then you can kind of fly through the scene, you can see how good it looks. And here you can see there are some missing data pieces in the, in the windows and so on. I guess these are actually holes in the real environment, but you can see the patches are not like totally perfect around the edges of things, but on the surfaces things look really good. And I think we can skip forward to, here's a reconstruction of Venice. So again, around the edges of objects, you see a little bit of noise along all these kind of spikes and towers, but on the actual surfaces of objects, things look really good. And then once you've textured the objects, things look even better, right? And so this is really, pretty impressive. And again, this is possible because of the zillions of tourist photos of these places that you can put into your massive multiview stereo algorithm, right? And so the details of, how do you choose which images you should use as the basis for your MVS algorithm, there's a lot of good work on that also. And so now, this is not to say that you would just be able to pop this onto your computer and do it in a few hours. I mean, this is like, I think I mentioned in a previous lecture, there was this kind of building Rome in a day paper. The idea was that you could take all these tourist photos of Rome, and then how many, if you had all the clusters, of computational power in the world, how would you try and get the 3D reconstruction done in 24 hours, right? But that was not 24 hours of a single computer, it was 24 hours of like a ton of computers. Although lately it's come down to be a little bit more commodity. Like you can now download, for example, there's this nice thing called Visual SFM. So basically, one nice thing about this patch-based multiview stereo, PMVS, is that he made this publicly available. And so lots of commercial, or not some commercial, lots of kind of hobbyist stuff is built on top of the system. And so this Visual SFM is a very nice way of just simply dropping images in, doing the automatic matching, doing the automatic 3D construction. And the matching, I think, may take a while. This is basically a real-time run of 3 minutes of watching it go. I'm not going to necessarily watch it for all 3 minutes. But the idea is it really is just as easy as kind of loading up some images, generating these correspondences, and then what you see is, like at some point, you see it's basically inserting every camera into the scene one at a time. You can kind of see, if you're reading this closely, there's stuff about bundle adjustment and number of 3D points. So basically, this is solving an incremental structure for motion problem, like the match moving problems we talked about in Chapter 6. And so after you solve all these one-by-one match moving problems, then you call basically this, execute dense reconstruction by PMVS, And now it takes a few minutes to go from these sparse points to a dense set of points. And that's a little bit harder to see, but you can see that at the very end of this video, they kind of toggle something where now this person's working in the dense world instead of the sparse world. You can see like all the holes between the points kind of click in. And so this is definitely something to fool around with if you're curious about doing dense reconstruction. Another thing, I guess, while I'm talking about it, so there are other things. Here's another like web-based multi-view reconstruction. So you kind of take your images and it uploads it to some server somewhere, and then it does it. One thing that's really well, actually, let me just go back for 1 second, finish up my lecture on the topics, and I'll come back to the tools. I saw a question though.
Is these the same guys who did phototourism?
Yes, the phototourism guys know Yasu very well, and so like there's definitely a big connection between that whole group of University of Washington alumni and this project, right? And so yes, so basically the PMVS sits on top of, I believe, this software from Noah Snavely called Bundler that basically is the heart of phototourism. It's basically like a large structure for motion, large-scale structure for motion from image collections thing. And so what you need to make all this work is you need to get Bundler, you need to get PMVS, you need to put it all together, but that's something that when it came onto the scene, suddenly it enabled kind of the average person to do multi-view stereo in a way that you couldn't have dreamed of doing before. And so I want to show one last thing at the end. So let me just finish up my technical part of the lecture here. This is just an example of a multi-view stereo result. The last thing I wanted to say, I guess, is that you can do things with, instead of trying to estimate the 3D positions of points, you can also think about this as trying to estimate a bunch of simultaneous depth maps from my images, right? So we know that basically it's kind of analogous to say, okay, for this point in this image, I want to estimate its physical 3D depth, right? And once I know that depth, then I can basically push forward this little block of pixels or this pixel and color that point in space, right? And so this is what I would call a depth map fusion idea. So the last kind of technique I would say is depth map fusion. And so the idea there is that, in each image, and I guess I can't really say much better than this picture. So in each image kind of takes turns being the reference image, and what I do is for every pixel in the image, I kind of hypothesize, okay, so what should the depth at this pixel be? So I push out a ray into 3D space and say, okay, well that's where the pixel will be from this camera's perspective if it was really there in 3D. Then I can project that back down onto all the other images and look at the neighborhoods of that pixel in the resulting images and say, okay, well, do these neighborhoods here match up with this neighborhood over here? And if they do, then that depth is a good candidate. And if they don't, then it's probably not the right depth. And so you can imagine that, very crudely what you could do is just kind of like optimize over this d of p for every, as a function of d for every pixel, and then kind of get estimates based on how consistent I see the corresponding pixel neighborhoods in these other images. So it's actually very similar to the idea of what we talked about with the surface-based reconstruction, where I'm kind of pushing forward points, projecting them back down to the images, and using the image-to-image matches as a basis for comparison. And again, you probably want to be smart about how do you, not just looking at squares or rectangles around the corresponding points, but also looking at, the deformed rectangles that come from perspective distortion as I, look at surfaces from very different angles, right? So I probably don't want to compare squares to squares. I want to compare squares to little squishy points, squished squares or fat squares, also known as rectangles, I guess. Okay, and I guess the last thing I would say about just general multi-view stereo is that obviously you can always do better if you kind of do a hybrid of just images and something like what we talked about last time. So if I were to also allow myself to project structured light into the scene, just put some light stripes in the world to give me some texture on objects, well then I can do even better, right? Because now I've got the best of both worlds. I've got, all the stuff that comes from stereo corresponds, and I've got kind of some introduced texture that I can use to help me with featureless regions of the world, right? Okay, so what I was saying here is that this has become very commoditized. And so here is this service from Autodesk called 123D Cache. Now on your phone, although it doesn't actually work on your phone. You take the pictures on your phone, right? So here this guy is going around as a kid. Now you basically upload them to a service, and you get a 3D model that comes back at you, right? And people kind of do this with their food and with their, here we go, sushi, and you can see that there are some places where you don't necessarily get all the data back, but then Autodesk has actually done a pretty nice thing where now you can print out these objects, so you can do some editing of the objects, and you can crop with planes and so on, and now you make the 3D printout. So I was talking about making action figures yesterday. So actually, probably if you're going to make an action figure, this is probably an easier way to do it than using the scanner that we had last time, right? Because then you've got this, So I don't know how much they charge you to print the object, but the 3D reconstruction part is free, right? So I downloaded this on my phone yesterday and made this model of my Totoro in the book, right? And so, I just went around and took, about 20 pictures, and here you can kind of see that things are not perfect. Like there's a chunk of texture that for whatever reason here it didn't get, and so you can kind of you're almost looking through the object. And you can also see that actually the book, right, is not super great because there's lots of weird. Looks like this book has been bashed around a little bit. It's kind of blended in with my my leather coffee table a little bit. So there are lots of reasons why this could be true. One thing that will defeat or mess up a multiview stereo algorithm is reflections and specularities. And so the book is shiny. This was on a day where there was light coming through the windows, and so the reflections on the surfaces of these objects are going to definitely confuse these algorithms that are trying to say are these things photo consistent, right? And so if you really want to do this the right way, you should try and control your lighting so that there are not a lot of bouncy reflections off of things, right? That's going to be a problem. But in terms of the Totoro, which is actually a matte object, I'm actually kind of surprised. Maybe this is just I didn't let it load long enough, but the 3D reconstruction of this guy is pretty good, except for you can see that it didn't really totally resolve the gap between this little tree branch and its head, right? So if I were to zoom in on this a little bit, right? So here, this kind of appears to be still a filled-in hole, whereas it probably shouldn't be. And also, you can see that there's some texture issue. Like here, the head of go away, kid. The head of this guy has some sort of a green leafy texture that again came from some sort of erroneous estimation of what the color should be at that surface. So the surface itself has got the right, it's got the right. I don't know how I get back to the non-zoomed version. Sorry, it's freaking me out. Maybe if I were to do this. Yes, okay, so now I'm back to the, sort of. I think yeah, here we go. Yeah. So you can see, not only did it get some of my table, but it also got some of my sofa that's further away, right? So it's kind of only giving me the patches that it was able to get good estimates for. But, this is definitely worth playing around with. And actually, if you were a little more careful than I was about taking pictures, it does work pretty well, right? One other thing that, kind of apropos of what's going on these days. So I don't know if anyone played this LA Noire video game. Was I the only one? All right. So LA Noire was this kind of very interesting facial motion capture situation where they had, instead of having a kind of animated face, it was an animated face, but basically what they did was they had all the actors perform with, I'll just let this play. They did all the facial expressions inside this multi-camera studio. So this is basically kind of like a multi-view stereo situation. And then they would stream a version of this captured dialogue into the game in real time, right? And so this is the original on the left, and the right is the motion captured thing, or the multi-view stereo thing. And so really what they're doing is they're estimating, real-time 3D position and texture. And I got to say that when you see it in the game, it really is very different than other avatars in video games, right? Like they had all of these. Of course, the idea was that part of it is that you're trying to look at people's expressions and tell, are they telling the truth or are they lying, right? And so part of the key is that they wanted to capture actors who were making these kinds of like shifty-eyed expressions and so on, and they, it actually I think was fairly successful. I mean, there were points where it was kind of uncanny valley, but there were a lot of points where it was also like, you could really buy that this was a person. And so like, as you watch towards the end of this video, it's not like it's some like kind of crummy CGI version of something. It really is the person's face that's been put onto these 3D models. Part of the part that was a little bit tricky was that the bodies were separately motion captured, and then they kind of stitched the moving heads onto these bodies, and also things like clothes and hats and stuff like that inevitably look a little bit weird. Like when you put the hat on the person, it looks a little bit like the hat doesn't seem to sit totally well. But that was really an impressive step forward. And unfortunately, I don't know that any other games have really gone on to do anything quite like this, because it was a huge undertaking for them to figure out how to make this work. But that was really one of the selling points of the game, was that you really got this sense of personality coming from the faces in the game. So yeah, it was pretty neat. So another thing that actually just came off the press is the new Google Camera app, which does basically on your phone refocusing or blurring of an image, right? And so so maybe some of you guys are familiar with this Litro camera. So the Litro camera is something that does this with what's called a light field in hardware. So it actually is generating a lot of different actual physical images of the scene, just a little bit separated, so that you can do kind of changes in parallax, little changes in viewpoint, little changes in refocusing, because it's got lots of actual images of the world, right? Whereas here you've only got one image of the world, or so it seems. What's actually happening is that you are basically asked to move your camera a little bit when you take the picture, and what it's really doing is a multiview stereo algorithm where it creates a depth map, right? And so in addition to having the picture, it has the depth associated with every pixel, and that's what lets you do basically interactive, refocusing of the image, because then they can say, okay, I know that all this stuff is closer to the camera, so it should be sharp, and all this stuff is further away, so I apply a little bit of a blur to it, right? So it's kind of like a software version of the Litro camera, right? And I'm sure the Litro people are probably a little bit unhappy with stuff like this, right? Because it really is, but if you look at what's underneath the hood, right, they're saying they're using structure for motion, bundle adjustment, multiview stereo, right? And so the key is that you don't just have a single image to work from, you have a series of images that you use to create the depth map, right? And so again, actually, if you look at this Google research blog, after taking this course, you should be able to understand pretty much everything that's in this paragraph about, first they do structure for motion, then they do bundle adjustment, then they do multiview stereo, and there's some interesting problems about how do you do this quickly on your phone, because unlike the 1, 2, 3 catch, this one is not farming anything out to the cloud to do computations. It's all doing it on the spot. So they have to have a fairly efficient structure for motion and multiview stereo algorithm to work on your phone. Okay, let's see if there's anything else I want to say here. Well, I think that that's pretty much it for the moment. So I would say that, again, if you want to know what's really the best multiview stereo algorithm at a given moment, then this Middlebury place is the first place to look for kind of understanding how good things are, right? And so you can sort basically by, whether you care about accuracy or percentage completion, whether you care about the view on all of the views or just a subset of the views. And you can see here these Furukawa 2, Furukawa 3. Furukawa is the researcher that I told you about before. I'm not sure if we have a mousing over any portion. Oh yes, here we go. So basically, these papers here by Furukawa are the original patch-based multiview stereo papers. And so you can see that these are still at the top of the stack. And so I think it's fair to say that patch-based methods are still pretty good. But I don't think that the I think I remember reading that the lens blur in Google Camera is actually a very computationally much simpler algorithm that actually probably is not very high on this list, but can run quickly on your mobile phone, right? And still, for the purposes of refocusing your selfie, looks good enough, right? You don't need to have like super accurate depth map to be able to do this kind of foreground background blur, because that's the kind of thing that you're taking a picture of, right? Usually, you're going to be sufficiently separated from your background that if the only problem is telling which pixels are in the foreground, I think you can probably do that pretty well with a relatively simple algorithm. Okay, so any questions about Multiview Stereo? So it really is worth downloading the Multiview, or downloading the Autodesk 123D Catch. There's a app on the phone. There's a desktop version, then there's a web version, and I had a hard time getting all three of them to play well together. But certainly you can get the phone stuff onto your web app, and then you can fool around with what's on the web app, right? And like I said, I'd be very curious to see the whole pipeline going from the acquisition to the 3D printing. I think that would be pretty neat. So, okay, so in that case, I will